The actual situation of lead alloy cooled fast reactors basically was given as an overview. Two systems actually are employed at time in Russia. This is the SVB 100, which should be in a running scheme in 2017, and the Brest 300, which is planned for the year 2022-25. In Europe, we have a Alfred demonstrator, which is planned to be starting construction 2019. So actually the site was decided to be in Romania, but still pre-licensing and pre-design phase are actually going on. Lead has some positive features. It don't react heavily with water and air. It has a quite nice high melting and a high boiling point. That means you just basically never run in the two-phase flow. And the third thing, you can basically have a relatively large core dimensions. That means you have natural convection capabilities during normal operation and also during decay heat removal. But lead is highly aggressive to the materials because solubility of the major alloying elements and steels is very high in the lead alloys. That means that you have to protect the steels, and it's done basically simply by oxidation, in situ oxidation in the lead bismuth, but this, or in the pure lead, but this basically recommends and needs a very precise oxygen control of your liquid lead. The steels that should be used for most of the components of 316L is capable to be used up to 480 degrees C. At higher temperatures, especially needed for the fuel clad and for the heat exchanger, you have to use different materials, or you have to adapt the materials by different measures. For the ferritic martensitic steels that should be used for the ELFR at the fuel clad and at the heat exchanger materials, you have the problem that you grow relatively thick oxide scales in short terms, so you have to reduce these oxidation by additional measures. There again, up to 450, you can operate as they are, but at higher temperatures you have to do something. What you can do is you can alloy silicon, aluminum in situ oxidation formers into the material or into the surface, and by that you can create thin protective alumina scales that grow slowly in time, or silicon oxide scales slowly in time, and are capable to operate these steels up to 600 degrees C. It's clear that these materials are not yet on the shelf to be bought actually, but a lot of effort is going on to optimize that materials, to optimize the production route, and to go on with that things. It's so far clear in 2016, 17 when they will, or 19 when they want to start the ELFR, we have to use the materials that are there at the moment. That means that might lower temperature at the output, but for the future, of course, improved materials might fulfill the requirements we have. Thank you very much.